Welcome to week 8 of pre-calculus. This week our plan is the following. We will talk a little bit more about logarithmic functions. Specifically, we'll talk about logarithmic properties. Then we will solve some exponential and logarithmic equations. That's an important topic. And after that, we will begin our long journey into trigonometry. We will start talking about angles. So the first topic is logarithmic properties. Let me remind you that the logarithmic function is the inverse of the exponential function b to the power x, where b is a positive number different from 1. Any exponential function with base greater than 1 or base between 0 and 1 is injective. And if you view it from the real numbers to the set of positive real numbers, it has an inverse called the logarithmic function. Remember the graphs of the logarithmic function. So there are two types of logarithmic functions, those with base greater than 1. These are monotone increasing functions defined on the entire set of positive real numbers. The image is the set of all real numbers. The key point is 1, 0. And likewise, the logarithmic function with base between 0 and 1 is monotone decreasing. As before, the domain is the set of all positive real numbers. The image is the entire set of real numbers. And the key point is again 1, 0. You can easily see that log x base b with b greater than 1 is symmetric about the line y equals x to the graph of b to the power x. That is because b to the power x and log x base b are inverses to each other. And the same for the case when base is between 0 and 1. The graph of b to the power x and the graph of log x base b are symmetric about the line y equals x. So that is what we talked about last week. Again, remember the domain of the exponential function which is also the image of the logarithmic function, is the entire real line. The image of the exponential function in the domain of the logarithmic function is the set of positive real numbers. Because they are inverses to each other, we also have these identities. B to the power log x base b. B here should be in the base. Is x, and log b to the power x base b equals x. The first identity is true for every x positive, and the second identity is true for every real x. So once we recall all these facts, we can now start talking about various properties of the logarithmic function. The first of them is the so-called product rule. You will see, by the way, that logarithmic properties mimic those of the exponential function. For instance, you know that the exponential function turns a sum into a product. The exponential function of a sum is the product of exponential functions. Logarithmic function does the opposite. It turns product into a sum. More precisely, if base b, as always, is positive and different from 1, m and n are positive real numbers, logarithm base b of the product m times n equals the sum of the logarithms of m and n, both base b. In a certain sense, it mimics the property of the exponential function to turn sums into products. Logarithm turns product into sum. Now let's explain why this is true here. Well, let's denote log capital M base b by little m, and log capital N base b by little n. So immediately, that means that b to the power lowercase m equals uppercase m, and b to the power lowercase n equals uppercase n. That is the very definition of logarithm. What does it mean to say that log capital M base b equals m? It means that if you were to raise base b to a certain power, hoping to get capital M, the power that you need to raise b is exactly little m. All right. Now, of course, we're going to use the corresponding property of the exponential function. Because if we write log of the product m times n base b, now that m is b to the power lowercase m and n is b to the power lowercase n, we can write m times n as the product b to the m times b to the n. Now, using the product rule for exponents, this product here equals b to the power m plus n. Now, from here to here, it's this identity, right? To get from line 2 to line 3, I'm using this identity, where instead of x, I have m plus n. And now to get from line 3 to line 4, I simply replace m and n by how they're defined. Little m is log base b of capital M, and little n is log base b of capital N. All right. Now a similar rule for quotients. It will mimic the rule that you know for exponents. B to the power x minus y is b to the power x over b to the power y. Note, by the way, that there is no danger of dividing by zero here because the exponential function never takes the zero value. B to the power y is always strictly positive. So the rule is this. The exponential function turns differences into quotients. The logarithmic function turns quotients into differences. Log of a quotient is the difference of logs. The explanation or the proof is very much similar to the proof we gave above. So we denote log base b of capital M by little m. Therefore, again, as before, b to the power little m is capital M. And the same trick for little n. Little n will be log base b of capital N. So by definition of logarithm, that means b to the power little n equals capital N. Now if we write this quotient, m over n, that's b to the power m over b to the power n, and now we're using the well-known rule for exponential functions. The quotient b to the m over b to the n equals b to the power m minus n. The exponential function turns quotients into, well, differences into quotients. Now again, from line 2 to line 3, we use that identity, that log base b of b to the power x is simply x, where instead of x, I have m minus n. And if I now replace m minus n by how they were defined, this is m and this is n, I get the desired result. This here is an important rule called the power rule. In a certain sense, it mimics the well-known rule for exponential functions. B to the power x time, then raised to the power y equals b to the power product x times y. So what does the rule say? Whenever you need to take log of a power, the exponent may come down. The exponent may come down. Now, why is this the case? Well, the easiest way to see that this is true is to actually check that when I raise b to the power alpha times log capital M base b, I actually get log m to the power alpha base b. Because again, what does it mean to say that log of m to the alpha base b equals this? It means that when b is raised to this power, I get m to the power alpha. Well, verifying that is simple because b to that power, I'm using this rule for exponential functions. When you raise base to a product, you can first raise b to, checking that indeed b to the power alpha times log capital M base b is m to the power alpha is easy, because we will be using this rule for exponential functions. When you need to raise b to the power, which is a product of some x and some y, you can first raise b to the power x, and then the result is raised to the power y. That is exactly what we're going to do here. We are raising b to the power alpha times log m base b, and I'm going to call this x and this y. So I'm first raising b to the power x, which is b to the power log m base b, which is of course m, by the very definition of logarithm. So what's left is m to the power alpha. Therefore, by definition, we get the desired result. Now, I should make an important comment about all these three rules that we've talked about. The product rule, the quotient rule, and the power rule. It's very important that when you apply them, you check that all expressions involved in your reasoning are existing. In the sense that, for instance, it's very easy to make a mistake when applying the product rule. For example, let me show you the following line. I'm going to compute natural log of 1, which of course we know is 0. On the other hand, definitely 1 is the product of negative 1 by itself. Negative 1 times negative 1 is certainly 1. Now, applying the product rule, I simply get ln of negative 1 times ln of negative 1, where neither exists. Natural log of negative 1 simply doesn't exist, because the logarithmic function is only defined for positive arguments. Of course, the mistake happened here, because I didn't check that my numbers capital M and capital N were positive, and they were negative, even though the product of M times N was a positive number. So again, always check that the numbers M and N here are positive, for otherwise you may fall into this trap. Same goes for the quotient rule. It's perfectly fine for the quotient to be positive, even though the numerator and denominator are negative. So before you write that the log of a quotient is the difference of logs, you definitely need to check that both M and N are positive. Right? I can run the same argument as before. Natural log of 1 equals natural log of negative 1 by negative 1. And that is natural log of negative 1 minus natural log of negative 1. Well, neither makes sense. Neither term makes sense. So the mistake here occurred because I didn't check that my numbers capital M and capital N were positive, and they were not positive. That type of mistake for the power rule is even more common. For example, it's very common for people to write ln x squared, and now applying the power rule, I can take the power down, right? That's what the power rule says. That when you take log of a power, the exponent may come down. So I can write that ln of x squared equals 2 times ln x. The power came down. It's all good, except that the sets of values of x for which these formulas on the left and on the right make sense are different. The formula on the left makes sense for any x except 0. In particular, x here could be negative. It's perfectly fine if x is negative, because if x is negative, x squared is positive, and natural log exists for every positive argument. On the other hand, on the right, I cannot allow x to be negative. I must have x to be positive. So one has to be very careful with formulas like this. Always keep track of your domain. If you want x to be non-negative in both sides, the right way to do this is to put the absolute value here. Now, in both sides, on the left and on the right, the only requirement on x is that x be non-zero. Because again, if you have ln of -1 squared, which is a perfectly valid number, -1 squared is 1, and ln 1 exists. But if I were to thoughtlessly apply the power rule, that would have given me 2 times ln -1, and that doesn't exist. So you have to be very careful. Always check that all expressions you are writing actually make sense. All right, so let us practice some of these rules in these examples. And again, we have to absolutely remember to always keep track of when our expressions make sense. So in the first example, we need to rewrite this natural log of a quotient as a sum or difference of logs. Well, we have ln of x to the power 4 times y over 7. Now first, applying the quotient rule. The denominator is positive, so this whole thing only makes sense when the numerator is positive. We must have x to the 4th times y greater than 0. Provided that, we can write the given logarithm as ln of x to the power 4 times y minus ln 7. That is the quotient rule. Now, if we want to apply the product rule to the first term, we should check whether this is permissible. We should require that before we write that this is ln x to the power 4 plus ln y, we should make sure that x to the power 4 and y are positive. X to the power 4 is positive if and only if x is non-zero. And we also need y positive if we write that. So this here is the product rule. And now to apply the power rule to bring this power of 4 down, we must require that x is positive, because then we will write 4 ln x plus ln y minus ln 7. This here needs both x and y positive. Let me add a page here. So again, in this example, we just had that ln of the quotient x to the 4th y over 7 equals 4 ln x plus ln y minus ln 7. That is for any x and y positive. But what if x and y are actually negative? X could be negative. In fact, all we need for this expression to make sense is that x to the power 4 times y over 7 be positive. But that is if and only if x to the power 4 times y is positive, because the denominator 7 is always positive. And that is if and only if x is not 0 and y is positive. So in particular, x could be negative. So how can we simplify this without placing heavy restrictions on x as we just did? You see, when we wrote this is correct. But we placed a very strict restriction on x. We had to say that x is positive, where in fact x may be negative in this expression. So the way to go with this is to say that ln x to the 4th times y over 7 is ln x to the 4th times y minus ln 7. So far we have the same steps. Now, because y is positive, the next step will be the same too. Ln x to the 4th plus ln y, which is all right because y has to be positive. But now, when I put the 4 down, I won't require that x be positive. I will allow x be negative, but I need to write the absolute value of x. So there will be 4 times ln absolute value of x. This has the advantage that Now we don't require that x and y be positive, we only require that x be non-negative and y be positive. So now the restrictions are not that heavy, because this places a heavy restriction. At least they're heavier than the ones on the left-hand side. So again, it's important to keep track of your restrictions. You need to know when your expressions make sense. In the second example, we need to expand ln of x squared times y cubed over z to the power 4. And again, it's easier if you first ask that question. When does this expression make sense? This expression makes sense, the logarithm makes sense if and only if the argument is strictly positive. Well, x squared is always positive. Well, this is a fraction. The fraction is positive if and only if both the numerator and the denominator are positive or both are negative. Z to the fourth cannot be negative, it's always positive. Z, though, could not be 0. X could not be 0. And if x is not 0, x squared is always positive. So the ratio of x squared over z to the fourth is always positive. And the sign of this expression is entirely determined by the sign of y. Y has to be positive, because if y is negative, the entire thing is negative. So under these assumptions, we can work out the original expression. We can first apply the quotient rule to write that this is ln of x squared y cubed minus ln z to the fourth. That is the quotient rule. Now, I mean to apply the product rule here and the power rule here. So I will have ln x squared plus ln y cubed that is permissible because y is positive and so y cubed is positive, and x is non-zero and so x squared is non-zero. But if I just write minus 4 ln z, I am now in trouble because z here is allowed to be negative. I can't do that. Or if I do that, I need to require that z is positive, which is unnecessarily heavy restriction on z. There's no need to make z positive where in the left-hand side it's allowed to be negative. So the way to go is to put absolute value. Now I apply power rules for each of the first two terms. To get 2 ln x plus 3 ln y, and I need to stop and think if I'm now again in trouble. I am in trouble because x is allowed to be negative, and here x absolutely cannot be negative. This is fine because y is required to be positive. Let me just write here that I use quotient rule plus product rule plus, power rule. And here I used power rule. But I absolutely need to say that x is taken by absolute value. And that's it. This expression exists for exactly the same restrictions on x, y, and z as the original expression. Y has to be positive, x has to be non-negative, which is all right. If x is negative, x has to be non-zero, If x is negative, I have x by absolute value, so it's okay. Z also has to be non-zero, and if z is negative, I am all right here because I take z by absolute value. So my advice is do these problems slowly. Always check if what you write makes sense. Now, the next example was expand ln of or log of root x. Again, if we think about the domain of this function, root x has to be strictly positive, which is equivalent to x being strictly positive. And now when I write root x as x to the power 1/2, I can apply the power rule, there is no problem. And write 1/2 log x. This time there is no need to put the absolute value because x is required to be positive. I forgot to write restrictions on x, y, and z in the previous problem, which is very important. For any x non-zero, for any y positive, and for any z non-zero. In our current problem, this is true for any x positive. In the next problem, we have log of cubic root of x squared. And again, the question is, when does this exist? We need cubic root of x squared to be strictly positive. Cubic root is strictly positive whenever its argument is strictly positive. And x squared is strictly positive whenever x is strictly positive. Whenever x is not zero. X squared is positive whenever x is not zero. So we only require that x be non-zero. And cubic root of x squared can be written as log x squared to the power 1/3, and applying the power rule, I can write that this is 1/3 log x squared. And now I need to be careful when I apply the power rule again to bring the 2 down. Because if I just write that this is 2/3 log x by power rule, creates a problem because now x is allowed to be negative. And log of a negative number doesn't make sense. So I need to put the absolute value. And now the requirement is the same as for the left-hand side. Any x non-zero. All right, in the next problem, we need to expand log base 6 of 64x cubed times 4x plus 1 over 2x minus 1. And again, we want to know the largest subset of the real line for which this function, this expression makes sense. So we want 64x cubed times x plus 1 over 2x minus 1 to be greater than 0. And that is a rational inequality. We need to find roots of the numerator and roots of the denominator. They are 0, -1, and 1/2. And these we draw on the real axis. And now it's easy to verify that for any x greater than 1/2, we can, for instance, write 10. This expression is positive. 10 cubed is positive, 10 plus 1 is positive, 2 times 10 minus 1 is positive. And then the signs alternate. So x is either greater than 1/2 or in between -1 and 0. In particular, x is allowed to be negative. So with these restrictions in mind, we can start algebraic manipulations. So we first apply the quotient rule. It will be log base 6 of 64x cubed times 4x plus 1. Excuse me, I saw the inequality incorrectly. I made a slip of the pen. That was 4x plus 1. So that's all right. The roots are 0, 1/2, and negative 1/4. When you equate 4x plus 1 to 0, that's negative 1/4. So when we draw the real axis, we need to draw 0, negative 1/4, and 1/2. And again, for x to the right of 1/2, we have this expression positive, and then the sign alternates. So x is either greater than 1/2 or in between negative 1/4 and 0. All right, now we apply the quotient rule to say that this is log of the numerator minus log of the denominator. Stop and think. This is all right because this requires that x be greater than 1/2, and that is something that we have. How about this? Well, if x is greater than 1/2, there's something interesting going on here. If we apply the quotient rule, we need this to be positive, and this is positive if x is greater than 1/2. But if x is negative, and x is allowed to be negative, this expression doesn't make sense, right? If, for instance, x is negative 1/8, 2 times negative 1/8 minus 1 is certainly negative. So this expression won't make sense. I need to use absolute value. How about this? Pretty much the same here. I should use absolute value. We'll take care about it later. All right. Now, I will apply the product rule in the first term because I can write that this is log 6 of 64x cubed, and again absolute values, plus log 6 of 4x plus 1 minus log 6 of 2x minus 1. We can further simplify this if we know this 64 times x cubed is 4x raised to the power 3. So I can write that this is 3 times log base 6 of absolute value of 4x plus log base 6 of 4x plus 1 by absolute value minus log base 6 of by absolute value 2x minus 1. Now, can we simplify it any further? We can, I could again apply the product rule to this term for x and write that this is 3 times log 6 of absolute value of 4 plus log 6 of absolute value of x. All right, so we have simplified it to this point. I can, of course, drop absolute value around 4. Now, can we drop any other absolute values? Well, x is either to the right of 1/2 or between -1/4 and 0. I must keep this absolute value because x could be negative. And likewise, I have to keep this absolute value because even though if x is greater than 1/2, I can drop this absolute value. For a negative x, I must keep it. How about this one? If again x is positive, I'm all right, but if x is in between, if x is greater than 1/2, of course 4x plus 1 is positive. But if x is in between -1/4 and 0, we still have 4x plus 1 positive. So 4x plus 1 seems to be positive always. I can drop this absolute value. But I cannot drop absolute value around x, and I cannot drop absolute value around 2x minus 1. Again, for any x, in the union of intervals, -4, 0, union 1/2 infinity. Of course, if you were to require heavier restrictions, you could get rid of all absolute values. For instance, if you require that x be positive, in fact that x be greater than 1/2, right? If I take the same problem and start solving it again with different restrictions, right? So we already said that we need all of that. But in fact, we may require that the following right-hand side exists. If I write this as 3 log 4 base 6 plus 3 log base 6 of x plus log base 6 of 4x plus 1 minus log base 6 of 2x minus 1. That will make sense for under heavier restrictions for any x greater than 1/2. Then there is no headaches with absolute value. You don't have to put any absolute values. If x is greater than 1/2, this is positive, and this is positive. So the answer depends on what is meant. If you want to keep the same restrictions on the variables as the left-hand side prescribes, you have to give this answer. If you want to introduce heavier restrictions, you may give an easier answer, because the left-hand side definitely exists for x's less than 1/2 too. For instance, the left-hand side will exist when x is negative 1/8, whereas the right-hand side doesn't exist. So we have to require that x be greater than 1/2. All right, and another example of this sort, where we need to expand a ln of root x minus 1 to x plus 1 squared over x squared minus 9. Again, before you start algebra, you need to understand when this expression makes sense. This expression makes sense if and only if the argument of the natural log is strictly positive. Well, because the square root is always non-negative, all we have to do is require that square root exists and be non-zero, and then the denominator be strictly positive. Right, that square root exists and be non-zero. Well, the square root exists and is non-zero if and only if the expression under the square root is strictly positive. This expression is always non-negative, so we must require that it's non-zero. We must require that 2x plus 1 is not 0. For if 2x plus 1 is 0, this whole thing is 0. Whenever this is non-zero, this factor is always positive, and then we must require that this factor is positive. Now, what does that give us? X minus 1 greater than 0 implies x greater than 1. 2x plus 1 different from 0 implies x is not equal to negative 1/2, which is automatically true when x is greater than 1. And this, x squared minus 9 greater than 0, means x by absolute value is greater than 3. Which means that x is less than negative 3 or x is greater than positive 3. X less than negative 3 is contradictory to x being greater than 1. So x must be greater than 3, which is stricter than x greater than 1. X greater than 3 will imply the previous system. Definitely x is not negative 1/2 then. Definitely x is greater than 1 if it's greater than 3. And certainly x squared minus 9 will be greater than 0 if x is greater than 3. So with this only simple restriction, we can now apply the rules that we've learned. Applying the quotient rule first, we get ln of square root x minus 1 to x plus 1 squared minus ln of x squared minus 9 you can now separate the square root. It's safe. Ln of x minus 1 times ln of this squared, right? If you take ln of or square root of 2x plus 1 squared, right? That's technically absolute value of 2x plus 1, but because x is greater than 3, that's simply 2x plus 1. So we have here ln of root x minus 1 times 2x plus 1 minus here we can factor x minus 3, x plus 3. Now by the product rule, that'll be ln of ln of square root of x minus 1 times ln of 2x plus 1. Here I can again apply the product rule and write that this is ln of x minus 3 plus ln of x plus 3. Here in the first term, the exponent can come down. I can write 1/2 ln of x minus 1. This here should be a plus. Plus ln 2x plus 1 minus ln x minus 3 minus ln x plus 3. And that is for every x that is greater than 3. Again, the left-hand side exists if and only if x is greater than 3. Under this restriction, we can safely drop all absolute values because x greater than 3 implies all these expressions are positive. All right. Let's continue our study of properties of logarithmic functions. And the next property is the reciprocal property of of logarithms. So what does it say? It says that when you take a log of capital M base b, you may flip this and express this as log b base capital M. For example, log 3 base 2 is 1 over log 2 base 3. This, of course, requires that both b and m be positive and not 1. The proof is very similar to the proofs we gave before. So let's denote the left-hand side by little m. So that means that b to the power little m is capital M. And now we take logs of both sides, base capital M. So on the left we have log base capital M of b to the power m, and on the right we have log base capital M of capital M. Log base capital M of capital M is of course 1. And here on the left I use the power rule. Little m comes down. I get m times log b base m equals 1. From here, m equals 1 over log b base m, and m equals log m base b. So it's an easy consequence of the power rule. Now, with this in mind, we can derive another useful rule. Let me clean the page. That when you take log m base a power, b to the power p, not just b, but b to the power p. P can come up front as a reciprocal. For instance, log x base 8, because 8 is 2 to the power 3, will be 1/3 log x base 2. That is often very useful. We can actually give two proofs of this. One is the following. As always, let's denote the left-hand side here by little m. So that means base b to the power p to the power little m equals capital M. Now we take log base b of both sides. So on the right we get log m base little b. On the left we get log base b of the left-hand side, b to the p to the m. Here we use the rule of exponential functions. B to the p to the m is simply b to the power mp. And now we apply the same identity we've been applying all day today. Log b to the power x base b is simply x. So applying this here, makes MP come down as a power, and we get log M base B, which stays, and MP on the left. From here, immediately little m, which is on the one hand, by its definition, log capital M of base B to the P, solving this for m gives me that m is 1 over P times log M base B. Very simple proof. Now, here's another explanation using the reciprocal rule. If in this formula m equals 1, we get zeros on either side, and there's nothing to prove. But if m is not 1, we can write that log M base B to the P is 1 over log B to the power P base M, because that's the reciprocal rule. Remember, reciprocal rule says that log Y base X equals 1 over log X base Y. That is, of course, if both are positive and neither is equal to 1. Now, in the denominator, we can immediately apply the power rule. And so P comes down as a factor. It will be 1 over P times log B base M. Now, 1 over log B base M, apply the reciprocal rule again, will simply be log M base B. This here we apply the reciprocal rule again. Very useful property. All right, the last thing for today is the change of base formula, which explains why in practice we don't need logarithms other than base E. We can always agree that all our logarithms are natural. Because whenever you have some base other than E, say B, you can express all your logarithms with any other different base. Log M base B is the quotient log M base C over log B base C. Of course, here again, B is positive, not 1, C is positive other than 1, M is positive. Whenever you have log 3 base 2, for instance, you can always write that this is natural log of 3 over natural log of 2. That is very useful. You can now not think about other logs other than base E. So how does this rule follow? As always, denote the left-hand side by lowercase m. So it means b to the power lowercase m is capital M. Now take log of both sides base C, where C is any positive different from 1. On the right, we get log m base C. On the left, we get log base C of b to the power m. Now the power rule, m comes down. we get m times log b base c equals log m base c. Now we recall that m itself is log capital M of base b. From here, immediately, log capital M base b equals the ratio of logs m and b both base c. We can now go back to the previous week to the problems that we solved in the end. Remember, we had here, for instance, log x plus 2 over log 4. These are both by base 10. Using the change of base formula, we were able to write this fraction as log x plus 2 base 4 and get rid of the log base 10. It's simplified the expression slightly. By the way, under the assumption that here x plus 2 is positive, we can actually simplify this further. Right? We can write that this is log base 4 of x plus 2 to the power negative 2 plus 1, and that's log base 4 of 1 over x plus 2 squared. X greater than negative 2. Here I use the power rule. Negative 2 was moved as an exponent here. Same was in the other problem. We had natural logs here of x plus 3 and of 7, and I was able to write this as ln of x plus 3, rather log of x plus 3 base 7. And if I were to apply the power rule here too, that would give me log base 7 of x plus 3 to the power 4. So that explains how we were able to simplify these two expressions in these problems. So that's it for today. We will start exponential and logarithmic equations tomorrow. Thank you.